Example 54. If the probability of losing money on a business venture is 20%, the probability of making money is 35%, and the probability of breaking even is 45%, what is the probability of not losing money? All right, so in example 54, we're actually looking at a problem that could be done in your head, and I'm sure that some of you are already looking at it and you know the answer already and you don't have to write anything down, and that's understandable. But I want to use this simple problem to introduce the idea of a complement, to show that there are two ways to work out probabilities like this. There's sort of a constructive way and then sort of a complement idea. The complement idea is to sort of find a probability that we're not interested in and use it to derive a probability that we are interested in. So let's go through the problem using this two-way method or two-way approach. So here's the forward direction, so to speak. If I'm looking for the probability of not losing money, right? And if I want to represent that, I can use L for the probability of losing money, right? So before we finish this problem, let's stop here and create a little notation. So I'm going to use the probability of L as the probability of losing money, right? So what was the probability that we lose money? It says if the probability of losing money on a business venture is 20%, so I have that information in the problem, it's 20%. That's a chance I lose money. And then it goes on to say the probability that I make money. Well, making money, I'll use a dollar sign for that, right? Making money is 35%. And then it tells me the probability that I break even. Let's use BE for break even. Remember, break even means you don't lose or gain money, right? That's a 45% chance. Of course, if you look at this, it covers what? The full gamut of possibilities. In other words, the sum of these things adds up to 100%, because that's all you can do in a business deal, right? You either lose money, make money, or break even, which means you don't lose or make anything. Those are the only possibilities that exist. So the probabilities here have to add up to 100. So what we're going to do now is to look at this probability, and we're going to do it in a constructive way. And what I mean by that is we're going to add up all the ways that you cannot lose money. So what's the probability of not losing money? Well, that's the same as saying what? That we do the probability of make money, right? Make money, or break even, right? Isn't that true? Isn't that the only way that you don't lose money? You make money or you break even? Because anything else would be losing, right? Either you make money or you break even. Now, the word or in probability means to add. So when I say that I'm looking for the probability that we make money or break even, then it would be the probability of making money, which we said would be the dollar sign, plus the probability of this breaking even probability. And so the answer is just simply to sum these together, 0.35 plus 0.45. And that solves the problem. And if you do that, you get 0.80. You get 80%, right? All right, good. So that's the answer to the question using the forward approach, where we add up all the cases that make this true. How do you not lose money? Two ways. You either make money or you break even. If you add those probabilities together, you get the answer. Now, that's a perfectly suitable way to do the problem. However, you might have already stumbled on to a faster way to do the problem, which is to say what? The probability of not losing money could be written a different way. You could say, well, not losing money. Well, if this is losing money, right? Then the probability of not losing money can just be represented like this, right? A bar over the L means not whatever's here. So if L stands for losing money, then not lose money is that notation. And now I want you to look at some formulas here that I've shown. There's a relationship that says if you take something and add the complement of that to it, the probabilities must add up to 100%. You know this formula already, right? If I were to say to you, hey, there's a 20% chance of rain outside today. So if I said, hey, there's a 20% chance of rain, and I asked you, what's the chance it doesn't rain? The chance it doesn't rain, you would say is 80%. Now, how do you know that? Because you're saying to yourself, well, it either rains or it doesn't rain, so the two must add up to 100%. If it's a 20% chance of rain, the chance it doesn't rain is 80%. So you figured it out. You basically invented this formula in your mind just now, didn't you? Because if we were given the chance that it rains, if we take 100% minus the chance it rains, which was 20%, we must be given the chance that it doesn't rain or not rain, right? And vice versa, if I said there was a 10% chance it doesn't rain, then there must be a 90% chance that it rains, right? Because not rain and rain together must add up to 100%. So you know this relationship intuitively. So it follows here the same way. If you look at the pattern, whenever there's a not above on this side, then that's equal to 1 minus the probability of that same thing without the not, right? 1 minus the probability of the same thing without the bar on top. But we know this number, it's right here, it's 20%, right? So we're basically saying, hey, the probability that we do not lose money is equal to 1 minus the probability of L, which is 0.20, and that's 0.80. So the probability of not losing money is 80%. Same answer we got above. This is sort of a backdoor approach, right? Because what I did is I used the probability of losing money to get the probability of not losing money. So I kind of went at it sneaky. I went behind the scenes and got it in a backdoor way. Sometimes this is a very helpful way to do the problem. I would argue that these two approaches here in this case are equal, right? This didn't take a lot of work to do, and this didn't take a lot of work to do. You may have thought of this naturally, or you may have thought of this naturally, and I wouldn't say that anyone had the advantage there. However, sometimes there are dozens of things that would add up to make something true. Maybe, in this case, there's only 2 ways to not lose money, but what if there had been dozens of events that make this statement true? We'd have to add up dozens of probabilities. And more importantly, we'd have to calculate those probabilities often first, just so we would know what they are. We're not always given to us like they are here. So in that case, it's sometimes easier to work with this approach, because this approach only has one probability that it needs to depend upon, right? So you could just calculate that one probability and you should be able to derive the one you're looking for. So a lot of times this complement idea, this backdoor approach, is going to lead to a much simpler way to solve the problems. So we're going to use that in the subsequent examples, and you'll see that sometimes this backdoor approach is very necessary.